name's Carola.
And welcome to another video in our series of computational geometry concept videos, in which we take a geometric concept and we dive into its definition, history, and other interesting properties.
Today's concept is triangulations.
This is Lake Pontchartrain, and we are in Fontainebleau State Park, just north of New Orleans, across the lake. And this is the result of Hurricane Ida, which struck New Orleans and much of the surrounding area in the summer of 2021. Hurricanes are a major threat in much of the southern United States, and hurricane prediction is an important challenge. Researchers in oceanography and meteorology use computer models to study the creation and development of storms. One issue here is that computers work with discrete binary data, but these models represent continuous phenomena in the real world. So we need to discretize the space. And one common way to do so is by using a triangulation, a subdivision of the plane into triangles. The assumption here is that within each triangle, the conditions stay more or less the same. So to run one of these models, we only need to do a small amount of computation per triangle.
A triangulation is a maximal plane geometric graph. What's a plane geometric graph? Well, that's a set of sides in the Euclidean plane where pairs of sides are connected with edges that are straight line segments between them in such a way that no two edges intersect. And then the edges divide the plane into regions which we call faces. If you want, you can watch our video on plane geometric graphs over here. Now, if we start with a set of sides and arbitrarily add edges between pairs of sides, as long as those edges don't intersect, if we cannot add any edges anymore, then we have a triangulation. Now, a triangulation is a maximal plane geometric graph, meaning we cannot add any more edges to it. Note that there are many triangulations of the same set of sides. So if we start with a different set of edges, we'll likely get a different triangulation. So why is it called a triangulation? Well, another way to define it is as a plane geometric graph in which all faces are triangles. But actually, why are these definitions the same? We cannot just define the same thing in two different ways. We have to prove that they're equivalent. So let's do it. We're proving an equivalence. So that means there are two implications, so two parts of the proof. Let's start with one direction. So if all faces are triangles, then we cannot add any more edges. Why is that the case? Well, this is actually not too difficult to see. Since edges cannot intersect each other, any new edge we insert needs to be inside an existing face. But all faces are triangles, so if I want to insert another edge there, how can that be? A triangle just has three different edges and they're there already, so we cannot add another edge to it. Now for the other direction, we need to prove that if we have a graph where we cannot add any more edges, then every face is a triangle. And we're going to prove this by contradiction. Suppose there's a face in my graph which is not a triangle, but a quadrilateral. So it has four sides, A, B, C, D, and it's part of a larger graph, so there's other edges there like that as well. And now I claim that we can add either an edge between A and C or an edge between B and D. Or if the quadrilateral is convex, which means that all angles are less than 180 degrees, then we can actually add either of the edges AC or BD. And if the faces are even bigger, then there are even more ways to add more edges. So a triangulation is a maximal plane geometric graph or a plane geometric graph with only triangular faces. And both of these definitions are equivalent.
How can we compute a triangulation of a given set of sides? Well, we can just follow the definition and keep inserting edges until it doesn't work anymore. But how long does that take? Alright, so let's say we have n sides in total. Well, let's say we start by listing out the edges. So that's in the order of n squared edges. Or to be precise, it's n times n minus 1 divided by 2 edges. And so in this case, n equals 6, and so the number of edges is 6 times 5 divided by 2 is 15 edges. So then for each edge, we will try to add it to our existing graph. But to do that, we'll need to test whether it intersects any of the edges we've already inserted. So in the beginning that's not too bad, but after a while the number of edges we've already inserted can grow pretty large. So potentially, for every edge we encounter in our list, we might have to check it against a linear number of existing edges, whether they intersect. So in total, this algorithm takes, well, it's a quadratic number of edges, and for each of them we have to do a linear number of tests, so that's n in the order of n to the third time. So if you've been watching our videos, I'm sure you can feel the question coming. Can we do this faster?
Triangulations are, as old as mathematics.
Right. I mean, they're kind of graphs, right? So certainly Leonhard Euler will have had something to say about them.
Right, yeah. So in the 18th century, he proved, few theorems.
And of course, people only started looking at algorithms much later, after there were computers.
Many algorithms for triangulations, they might have been so simple that people didn't bother writing them down, right? So there are algorithms, but they're not really attributed to anybody. So this is what we call like folklore, Mm-hmm. In the book by Satya Devadoss and Joe O'Rourke, they mentioned two simple algorithms, like one is the triangle splitting, mm-hmm. and the other is the incremental algorithm. But those are all really simple approaches, and they're not attributed to anybody.
Right. Yeah. So part of the reason could be that, I mean, a triangulation, there's not one unique triangulation, right? For one set of sides, there are many different triangulations. So the problem of computing the triangulation is not really well defined. And actually people were also looking at specific triangulations at around the same time. And yeah, if you have a specific triangulation, I mean, if you have an algorithm for computing a specific triangulation, then you don't need an algorithm for a generic triangulation.
Yeah, that's true. Exactly. So, yep, and let's look at one of those specific triangulations, like the Delaunay triangulation.
All right, so there are ways to compute a triangulation efficiently, but there are many different triangulations of the same set of sites, and not all of them are equally useful. In fact, the triangles you see here are all nicely shaped, and that's important when we want to run simulations, because long and skinny triangles are just less likely to have constant conditions in them than these smaller or more round triangles.
One of the most used triangulations is the Delaunay triangulation because it has nicely shaped triangles. And the Delaunay triangulation is the central concept in computational geometry. There are different ways to define it. For instance, it's the graph of all edges with the empty circle property. So an edge between two sites, A, B, fulfills the empty circle property if there exists a circle with A and B on it, such that no other sides are contained in the circle. So for this triangulation, let's check that all edges fulfill the empty circle property.
So how do we actually find the Delaunay triangulation of a given set of sites? Well, we could again try to follow the definition. So we just keep inserting edges one by one, and for each edge we try if it fits or not. But now instead of checking whether it intersects any of the existing edges, we have to test the empty circle property. But how do we actually test the empty circle property? So for example, if we have two sites, then, well, which circle do we have to test for emptiness? It could be this circle, which passes through those two sites. So if this circle is empty, then the empty circle property is satisfied. But if it's not empty, then there might still be a different circle which is empty. So we have to try maybe multiple circles. So another possible circle, or this one, or this one, or this one, or this one. And in fact, there is an infinite number of circles which passes through these 2 points. So we cannot just test them all. So it's actually not obvious how to compute the Delaunay triangulation at all.
One way to compute the Delaunay triangulation is to start with any triangulation and make local changes to it until we arrive at the Delaunay triangulation. And the operation we use for this is the so-called edge flip. To do an edge flip, we need two adjacent triangles that form a convex quadrilateral, meaning all outer angles have greater than 180 degrees. Now for such a convex quadrilateral, what we can do is we can take out the central edge, the one that separates the two triangles, and replace it by the other diagonal, the one that connects the other two corners of the quadrilateral. Note that after such an edge flip, we again have a triangulation of our sites, but with different triangles. By the way, why does the quadrilateral have to be convex? Think about it. Now, if we keep flipping edges, we could get lucky and eventually find the Delaunay triangulation. We would need to get pretty lucky for that, though. Well, instead what we can do is we can only flip edges if it improves the shape of the triangles. Now, how do we measure the shape? Well, we can take a circumcircle of the triangle, meaning a circle that goes to all three corners of the triangle, and count the number of other sites in it. So if we look at this quadrilateral here and look at the circumcircle of this triangle, we have one other side in the circumcircle. But if we now flip the edge and look at this triangle here, we'll have no side in the circumcircle. Now we claim that if we keep flipping edges such that it reduces the number of sides in the circumcircles of the triangles, we'll arrive at the Delaunay triangulation. If you like a good challenge, try to prove this claim for yourself.
So that algorithm you just described is the flip algorithm, which was actually already described in 1977 by Charles Lawson. And I think I have the report here. So it's interesting. This is software for C1 surface interpolation.
Oh, nice. Okay.
So in there he describes the flip algorithm for Delaunay triangulations.
Right. Well, but he probably wasn't the first one to describe it. I mean, it's a natural concept, you know, but...
Right, yeah, who knows? I mean, it's a natural idea. But one question is actually, I mean, this is an algorithm, but it's not so clear how long it takes, right? We just start flipping, and okay, we hope that eventually we reach the Delaunay triangulation, but how many flips do we need, or why would it even terminate?
Right, exactly. Well, Charles Lawson actually proved already that it terminates.
Mm-hmm. Yeah.
You know.
Yeah, but it is not a very efficient algorithm, as it turns out. So actually, Steve Fortune proved a quadratic lower bound on the worst case number of flips. So there are triangulations for which it takes a quadratic number of flips before we reach the Delaunay triangulation.
So are there any more efficient algorithms for this?
Yes, actually, not long after this 1977 report, people started to find more efficient algorithms. So the first one was actually discovered by two researchers independently in 1981. This was. Mm-hmm. So that was David Watson, I think.
Yeah, and Adrian Boyer.
Right.
Mm-hmm.
Yeah, and funnily enough, they submitted their papers actually to the same journal, and turned out to be the same algorithm.
Yeah, right. It's funny. Yep.
Oh.
And in '83, David Kirkpatrick came up with a very different algorithm, an incremental algorithm.
Right. Yeah, very different idea, but also a faster algorithm. And then also Steve Fortune again in 1986. He already published an algorithm to compute the Voronoi diagram, which is the dual graph of the Delaunay triangulation. And actually, if you want to know more about the Voronoi diagram, we have a video about that. So all of these algorithms can actually be used to compute the Delaunay triangulation efficiently, and they all take the same amount of time, or in the order of the same amount of time, namely n log n, so
right. Mm-hmm.
n times the log of it.
Exactly, yeah. Mm-hmm. Yeah, but they all use very different algorithmic paradigms
Right.
to compute it. So same runtime, but very different techniques.
So why do the triangles in the Delaunay triangulations have such nice shapes? Well, there is an alternative definition of the Delaunay triangulation. It can also be defined as the triangulation which maximizes the smallest angle in every triangle. So maybe you can imagine why this leads to nicer shapes. Triangles with nicer shapes tend to have more equal angles. For example, consider these two triangles. This one has angles of roughly 50, 60, and 70 degrees. But this triangle has angles of roughly 10, 60, and 110 degrees. So while the middle number is the same in both triangles, the fact that the numbers on the left are closer to each other leads to a nicer shape of the triangle. It means that the triangle is somehow rounder, it's closer to being an equilateral triangle. So again, we see that we have two different definitions for the same geometric concept. The Delaunay triangulation is the triangulation which has an empty circumcircle for every triangle, but it is also the triangulation which maximizes the smallest angle in every triangle. So why are these two definitions equivalent? Well, a full proof would take a bit too far for this video, but let me try to convince you. Okay, so now imagine we have triangulation, and in that triangulation we have two adjacent triangles that together form a convex quadrilateral. That means we can perform an edge flip on those two triangles. So now let's consider those two different triangulations, which are everywhere the same except for these two adjacent triangles, and let's only look at the triangles and forget about the rest of the triangulation. Alright, so now we have those four different triangles. Let's consider the circumcircles of all of those triangles and count the number of sides inside each circumcircle. In this case, there are 3 points in this circle. And for this triangle, there are 2 points in its circumcircle. For this triangle, there's only 1 point in its circumcircle. And for this triangle here, there are no points in its circumcircle. And also, let's have a look at the angles of the resulting triangles. So we can see that the smallest angles on the left look a little bit smaller than the smallest angles on the right. So what we can see here is that the triangulation on the left has triangles with bigger circumcircles, which means that, well, there's more room for more sides to be in those circumcircles. So intuitively, that means we're farther away from the Delaunay triangulation. But at the same time, we also see that the smallest angles of those triangles on the left are a bit smaller than on the right.
So by running simulations on triangulations that model the water flow in Lake Pontchartrain and in the Gulf of Mexico, we may be able to predict the formation of hurricanes, which will allow people to evacuate sooner. So while that may not prevent this kind of damage, at least you won't be here when it happens.
Congratulations! You made it to the end of another Computational Geometry Concepts video. We hope you enjoyed it and learned something.
Yes, so today we learned about triangulations, and in particular the Delaunay triangulation, which is arguably one of the most central concepts in the study of geometric algorithms.
Right, and if you want to learn more, we put links to all our sources in the description below, including a link to a video on the twin sibling of the Delaunay triangulation, the Warner diagram.
Yeah, thanks for watching, and see you next time.